So the chain rule is used when we have embedded functions. Essentially when the outside function is dependent on the inside function. So basically what happens is we multiply the derivatives of the outside to inside functions. If you take a look at using the dy notation, the overall rate of dy by dx is going to be equal to the outside rate. So we have the outside rate as a function of the next inside function times the rate of that function with its embedded function times that function with respect to x. And when we look at this, when we multiply these rates together, I want you to notice something here, is that these terms du will cancel out. dv will cancel out, and what we end up with is dy divided by dx. So when we multiply these rates, first of all, the products of rates give us the overall rate of dy by dx. It's algebraically consistent, but not only that, it works just like we do in rate analysis in science. It's the exact same thing. So when we have embedded functions, we multiply the rates because the overall rate is dependent on the partial rates of each embedded function. So let's take a look at how we apply this. So we're going to do this very formally and piece by piece, but as we do more of this, we want to develop some fluency in doing this without having to write all of this extra notation. We're just going to differentiate outside in. But looking at this, the outermost function is the cube root function. So I'm going to write this as cube root, and the inside variable is going to be u. And that u is going to be defined by the red part of that expression, which is square root plus 1. So when we define u in the next line here, the next line, u is the square root plus 1. And inside that u function is another embedded function. I need to just give myself a little bit more room here to write this. So inside the u function is the next embedded function, which is v. Okay, and then that v is going to be defined by 2x plus 3. And so when we differentiate the y function, we get 1 over 3 u to the, this becomes u to the power negative 2 over 3. Differentiating the u, we get u prime, so I'm going to call this y prime. Y prime is equal to that. U prime then is equal to 1 over 2 root v. And then the final embedded function, v, the derivative of v is just going to be 2. So we're just going to multiply by 2 at the end. And so the overall rate, dy by dx, so dy by dx, is going to just be equal to the outside rate, 1/3, u to the 2/3, times the inside rate, 1 over 2 root v, times the most embedded rate, which is times 2. So it looks like this, and then when we expand this, and again, we want to try to avoid using this u notation and v notation. When we differentiate this, we want to differentiate outside in, and we end up with 1, sorry, I'm going to do this by color here. The outside function, we differentiate 1/3, and then looking at the inside expression, this is going to be root 2x plus 3 plus 1 to the power 2 over 3 times 1 over 2 square root 2x plus 3 times 2. And it's the exact same thing as we've done here. We've multiplied and just writing the notation in. This is dy by du. this next function in here is going to be du by dv, and the last function is dv by dx. And we can see that those terms cancel out, and we end up with dy by dx. And so this expression then, differentiating outside in at the very bottom, represents the derivative dy by dx. So essentially, the derivative of a composite function is a product of all the derivatives of the components. So we differentiate the outside, leave the inside undifferentiated, and then we work our way down to the most innermost function.